So, good morning. Welcome to Krishna's classroom. We have got all the ingredients now to define the integral. That is our objective. Yes. We have introduced a measure space. That means a given set with a sigma algebra defined on it, and then define a measure on it. So that is where we stand now. We have x from x to x. B is a or M is a sigma algebra on that. Then the next stage is mu a measure. Mu a measure it's a non-negative set function defined on the sigma algebra M. Okay. With the property that it is countably additive. Further, at least for one element of M, mu is finite. Okay, so mu is a map from the extended half line. It's a non-negative one. Secondly, mu is countably additive. Now, for some set, at least one. Mu A is finite. Then we explore the properties of mu. Now this is what we call a non-negative on the measure space, this is a measure, and xm mu is called a measure space. Xm is called a measurable space. That means only when you introduce a measure on that, it becomes a measure space. Right? Okay. Now then there are all the properties of measure that we have explored last time. I don't want to recall that. For instance, you can prove that mu of phi, the empty set, is equal to 0. That is one property that you can prove. Then mu is finitely additive. Finitely additive. These are some of the properties that you can prove. The point is that on some sets it is likely to take the value infinity also. For instance, on the real line, when we define we had for the half interval, the Lebesgue pressure is infinity. So it is there. It's the whole R is a part of the Lebesgue pressure. So those properties are the ones that you can derive from the conditions that we have already set. It's countably additive, this one, and together can actually no problem. But what is not there, because we are not assuming any additional structure on X. As long as it is not there, you cannot talk about translation as we did in the case of the real line, where you had Lebesgue measurable sets, and then if you translate the Lebesgue sets, you get a new set which is again measurable, and the Lebesgue measure of the original set with its translation are the same. So these kind of properties are there in addition to what you have for this, but such things are meaningless to talk about unless you have some additional structures on X, which we don't assume. So we are taking a very general, and as we go on and take up specific case situations, we can get such properties or impose such properties. Okay. Right. Now, what we want to do next is we want to define an integral of a measurable function. The consequence is that you can talk about what are called measurable functions in the usual way. And we have the nice properties of the measurable functions. That the sum of measurable functions are measurable. Okay. Finite sum of measurable functions are measurable. And if you have a convergent sequence of functions, measurable functions, they are measurable, and so on. They're all there. Then we also talked about a special class of functions, namely simple function. The simple function has the property that just the range is a finite set of real numbers, a finite set of non-negative real numbers that you have. Because we are going to talk about non-negative functions to begin with, and only after that we go to the general measurable functions. So, for the time being, we are only confined with non-negative measurable functions. That means we'll be working on which are later. Okay. Now, you have a simple function is a measurable function provided suppose a simple function is what? S is a simple function okay. So in fact it is a simple function, the range is finite. There, of course, you have, if you take, suppose the range of Define. Then we have defined AK contained in X such that AK equal to now S is measurable if and only if AKs are measurable. AKs are measurable. This is something that we can see. So we work with what are called measurable simple equations. Then we proved one very fascinating result that if F is a measurable on X, then there exists a sequence of simple functions one to infinity which are measurable. They are measurable, monotonic, and pointwise converging to that this is what you have 0, now there may be points. It's possible that there are points where at those points is increasing sequence which diverges to infinity. That is what happened. There are some points where the function may take a value plus infinity. At those points, the Sn has the property that it's an increasing sequence. In fact, the way in which we have constructed it will be take values 1, 2, 3, etc. So this which diverges to plus infinity. As you have seen, the elaborate construction we have seen, and also we have proved everything related to that. Okay, this is the setup where we stand now. Now we are in a position to define the integral of f. But before that, we'll recall, I think we have made a mention of it earlier also. We'll just recall the arithmetic on 0 infinity. You know the arithmetic on the half-life, but when we extended half-life, we would like to have some clarity about the arithmetic because we'll have to use it. Okay. So, where do we stand now? Let me write. Or in short, what you are asking for is how do you extend addition and multiplication to the infinity also, because this is essentially you have put the point at infinity also. Now how do you extend? You have already, we know what it is here, that remains as it is, but how do you extend here? Now this is what we do. So we define a plus infinity for 0 so even when a is infinite, infinity plus infinity is taken as that, and further you have a into infinity equal to infinity into a, that means it commutes. This is equal to infinity for now what happens when a equals 0? This is the important thing. This is how we define multiplication. When 0 is multiplied by infinity, you get 0. It is set as 0. So also infinity into 0 is 0. Now this is such the requirements that we need while defining integral. Okay. So I'll just tell you how it is. You have suppose you have a singleton point where the function takes the value plus infinity. What is the area that you expect? The area that is covered by this is not considered to be indefinite or anything, but we take it as 0, which is something that is naturally suggested. Or at a countable set of points, suppose the function takes the value infinity. Now suppose you take a function which takes the value 0 everywhere on the real line except at the integer points. Okay, so we take x to be infinity. Now we define the function phi to be equal to 0 integer point, non-negative integers, and in the complement of that we take the function to be 0, and this is the function that we look at. So what you have at all integer points you have some lines, and suppose you want to talk about the area enclosed by what is that? Now this is where the problem comes. You know that this will turn out to be, by our definition, we are just this is the measure of the, let me write here, that is the set of integers, it's a measurable set, times infinity. But then, okay, we are taking mu to be, okay, we take mu to be the equation. Then mu of n, because it's a countable set, equal to 0. Therefore, this area is going to be, so this area which we would like this to be equal to 0, or that is the natural thing that comes out. Okay, so that's roughly the motivation. Now we can just make a remark about the arithmetic that we have done, or we have imposed or extended to the extended half line. We observe that the extension is consistent in the sense that it is very definite, in fact, very definitely defined. That's the first thing. It's not that you are defining 0 and infinity, some infinite, some finite, or indefinite or anything. We are just fixing it as 0. Now we observe that with this definition, we have the arithmetic that you have defines, or this both addition and multiplication are commutative, associative, and distributive. This means commutative means A into B equal to B into A plus B equal to B plus A. Associative means A plus B plus C, A plus B plus C equal to A plus B plus C. So that is associative, and the distributive property is A into B plus C equal to AB plus AC. These three usual properties of addition is also valid on the extended half-life. And here we are not assuming A or B to be A, B or C to be finite. I mean, one of them or more than one of them could be infinite. Now you see that A plus B equal to A plus C implies B equal to C when A is less than. So also AB equal to AC implies B equal to C this is the system. Okay. Further, you have this property A1, A2, etc. or AN is a sequence, it's a monotonically increasing sequence. Is a sequence with the property that AN converges to A, BN converges to B, which may be infinite also. So you may have a divergent sequence. Then AN so these are some of the consequences that we. Now with these definitions, we can now talk about sums, products of measurable functions are defined and they are measurable. So that's the definition. So that's about this arithmetic. This is what we have. Now we introduce the definition of the integration. the integral. We adopt the same strategy that we had in the case of Lebesgue integration theory. I mean, what you call, when we used Lebesgue measure on the real line, and whatever we did on the real line is now going to be mimicked here. Okay. What did we do there? Recall that we approximated the measurable function or the non-negative measurable function by a sequence of simple functions, which point-wise converge to the given function. That's one thing. The second thing is that such a sequence can be chosen as a monotonic sequence. Okay, so you can approximate, if you are talking about a non-negative measurable function on the real line, this can be approximated from below by a sequence of measurable simple functions. Okay. So what was the natural thing that we did? So you have a sequence of non-negative simple functions converging to f, and each Sn you have this property f. Now what we do is we define integral Sk with respect to the Lebesgue measure. Okay. So if E is a measurable set, then you get a non-negative sequence of numbers. Okay, it's a monotonically increasing sequence of numbers. So you have this property then we define the integral This was our strategy. We are going to do exactly the same thing. Okay. So let us formally do that. So integration of measurable functions all these structures are already assumed. Okay. Now mu is is a non-negative x on the measure space. That's our assumption. Now definition. If S is a non-negative measurable simple function, then it is of the form S equal to one to n alpha I ai, where ai, the set the characteristic function of ai, where this is true. AIs are assumed to be measurable. That means AI is a measurable subset. Then S takes these are distinct values, and on AI first we assume alpha I is different from alpha. So that's what we call a simple function. Okay. So that means on AI the function takes the value alpha. Okay. So A1, A2, AN are measurable subsets, and further AI intersection AJ is empty. Okay. So you have this problem. Yeah. Now we have what we have is this. We know that as we have said that Okay, we will come to that later, but before that, let us define the integral of S. Let that means E is a measurable subset of X. That's assumption. Make. Now we are in a position to define the integral of this. Then integral over E is defined as summation of alpha I mu of AI intersection. This is the definition of the integral of the simple function. Okay. So if S is given by this one, then integral of S is defined this way. So that means this is 1, S1, S2. So in this definition we use the convention, because here we use the convention. Use the arithmetic. Zero infinity and use Q. That's important. Wherever such a term comes, and one of these factors, either alpha I or mu of AI intersection E is 0, then that particular contribution from that term is 0. So that's the definition of the integral of a simple function. Now what do we have? We have already shown that there is a monotonically increasing sequence Sn that you can construct, which are simple functions which converge pointwise to the given function or diverges where the function takes the value infinity. So we shall use that. We use the power of the theorem. We know the existence of that. So we are now inclined to define the following. If is measurable and E is measurable. That is, E is an element of the sigma algebra M. Then define integral over E of f E mu as the following. The supremum of over E, where S simple Now we know that there exists measurable, non-negative, simple functions which are bounded by f. We have in fact explicitly constructed one. Such functions you take. Now you see that we have defined integral over E of S d mu. This we know. Okay. So corresponding to each S, there is a integral well defined. So that gives some numbers. Now you have a set of numbers, and these numbers may be bounded or unbounded. But possible that it is unbounded also. Okay. Now what we define, or what matters is that the supremum of this set of numbers exists either as a finite number or as infinity. And that supremum is what you define as the integral of f over. Okay, so what are the requirements? E should be a measurable subset of x, or E should be an element of the sigma algebra that you have put. And then integral over E of f d mu we can define. F is assumed to be measurable, and we know that there exists simple functions which are less than or equal to f. Okay, and for simple functions we have defined for any E, any measurable E, integral S d mu. Now you take all possible such simple functions which stay below f. Okay, then this integral would give you a subset of the non-negative numbers. Okay, now this set may be bounded above or bounded above by infinity, bounded above by a finite number, or bounded above by infinity. In any way, what is known, what we know is that the supremum exists. Okay, that supremum is what you define as the integral of f. So this is the definition of the vector. Okay. Now integral of f with respect to the measure mu. It's called the Lebesgue integral of f on the real line. We had specifically constructed a measure which we call the Lebesgue measure. So this need not be a Lebesgue measure. There is no, on a general X, there are no structures to support lot of other properties that are available for the Lebesgue measure on the real line. Okay, but it follows the same route, and therefore we just call it the Lebesgue integral. But Lebesgue integral, this is not complete here. Lebesgue integral of f with respect to the measurement. So, depending on the measure that you define, it is going to be different. Okay. So, there is a lot of versatility now. There, of course, we had our interest was to generalize Riemann integration. Okay. Then we went beyond considering intervals for which the length is automatically defined, but we introduced the concept of lengths or generalize the concept of lengths to a larger class of subsets of R consistent with the definition of intervals. Okay, so that was the Lebesgue measure, and once we defined the specific Lebesgue measure, so it was an elaborate job of defining it. Okay, then of course we are now going to a general switch, and we start with an x. On x we are not assuming any structure at all, unlike R, and we successfully define a sigma algebra on that. We successfully define a measure on that. In fact, there is versatility from both. Okay, so it depends on the measurable sets that you introduce. According to your requirement, you can do that, but it should have the sigma algebra structure. And then on that, you need this non-negative, countably additive function defined, which you call a measure. And once it is a measure space, on that you can talk about measurable functions, and then we can talk about non-negative measurable function for which the integral can be defined. At this stage, you might wonder why you are restricting to non-negative measurable function. The problem is this. First, you can talk about general measurable functions by splitting this into the two functions, f plus and f minus. And this we have defined f plus, if f is measurable, f plus is measurable, f minus is measurable. Both are non-negative, and in this case we can now define provided, of course, there is one case where it is not defined is when both becomes infinite and there is a difference. Now it is not defined. Otherwise, you see that when one of them is infinite, doesn't matter, the integral is valid. Okay? You get either plus infinity or minus infinity, also could be the value of the integral in that case. Okay, so in all other cases everything is fine, and this is the most desirable definition of the integral, which is consistent with what we had been doing all along. Okay, so that's why we'll finally tie up everything, but before that we'll confine ourselves to non-negative measurable functions. Okay. And now the question that might come is this: suppose f itself is a simple suppose f itself is a simple measurable function. One would naturally ask the following question. You have two things now. One, definition of integral, by 2 as a simple fraction. Then you have definition of integral by 3. We have taken as a non-negative measurable function. But when simple functions, when f is a simple function, the natural question is, are they the same? You can easily see that it is the same, because what happens is that if s is a simple function, okay, and if you consider all, you can still define a sequence of simple functions which approximate to this simple function. Okay, now you are taking and you see that the given simple function is going to be greater than or equal to all other simple functions that stay below this one, and therefore when you take the supremum, it is going to be the same. Okay, so the answer is yes. So there is no ambiguity about using these two definitions. So in the case of simple function, it will remain the same. Now, having done this definition, we can look at some of the properties of the integral. Okay, so first property, G, both f, G measurable. Now we have x measurable. Then what we have is integral over f Now this comes very easily, because you see that you look at all the simple functions that are lying below, so all s less than or equal to f implies it is also less than or equal to g. Okay, right? So there are more simple functions to come in between f and g possibly. Okay, so the supremum that you take in this case will be on a class of functions which are simple functions which are bounded below by f, whereas the supremum that you take, the corresponding supremum that you take here, is going to be below on all simple functions which are below g. It's a larger class of functions. Therefore, you see that the supremum is going to be have this inequality, and therefore what you get would be the integral would be less than or equal to integral. Now that's how you prove it. That's very simple. The remark is, every simple function s which is less than or equal to f is also a simple function which is less than or equal to f. The remark is, is also a simple measurable function. So, the supremum that you are taking is on a larger class of functions, therefore, naturally that integral is likely to be bigger than this, or that supremum is likely to be bigger than this. Okay. So, that is the argument. You can write down a formal proof for that. So, the second condition is if and P on then first measurable. Then what we have is this. That is also quite easy to work out. Okay. Because here what you have is the situation is A is contained in B, both A and B are measurable. Now, either work it as take F, and then what you have is this. You take, see, what you get would be F. You take the simple functions. You have a set of simple functions which stay below F over A. Okay. And then extend that as simple functions over to whole of B by setting the function to be equal to 0 on B minus A. That is possible. It's again a simple function which is below F on B. Okay. Therefore, once again the same kind of argument goes. Okay. You have a larger class of simple functions here, because every simple function on which approximates F from below on A can be conceived as a simple function which approximates F on B also. So once again the same kind of argument works, and you have the inequality. Now the third property is interesting. It says if F is a non-negative measurable function, next, and C is a constant such that it's a non-negative real number then what you have is this integral over E F. So this comes from the property that integral over E of Cs for a simple function S is equal to C times, use this, verify this, and then use this. I mean, it's very easy to verify this. It's not difficult at all. And once you verify this, you see that you are now getting approximations using this, where you can interchange this. Okay. So that's the strategy that you use. P as it is, E is a measurable set, F is a measurable function. Assumptions are that. Then what you have is this. Measure of E is integral that is again using the property that 0 into infinity equal to 0. This is where you definitely need that. Okay. Maybe the E, maybe the whole set X may have measure plus infinity, or E itself may be a set of infinite measure. In that case, what you have is that you look at this integral. Once again, you use the formula coming through the supremum of simple functions, and for simple functions you compute this, and we are assuming mu E is finite or infinite. Okay, so you go back to the formula and you easily see that the function is 0 on E. That means the value of the function on this set is 0. Therefore, in the sum that you come across, all the factors are maybe even if it is mu is infinite, it's going to be what is called mu. What is it? It's going to be 0 into infinity, which will become the value of the function is 0, and this is going to be 0. So all the terms are going to be 0. Therefore, the integral C. So that's very simple. These are all little things where proof is no problem at all. What you need is, you need to use the basic definition through simple functions. Another similar result, if mu of E is equal to 0, and whatever be the f, then for every measurable function, even if it takes the value on that's also very simple. It will be, in one case it is going to be 0 and infinity, in the other case it is going to be infinity and 0. The value of the function may be infinite, but the set, the measure of the set is going to be 0. Okay. F. If f is greater than or equal to 0, then integral over f du now you can easily see that if f is measurable, then and E is a measurable set. So f measurable and E is a measurable, then f is a measurable function and E is a measurable set, then chi E is measurable. And f chi E times product of measurable functions. F is measurable. So on any set you can consider, with this result, on any set you can consider the function to be an integral over x by actually multiplying by the characteristic function of chi E. I mean, this is quite easy. Once again, you can go to the basic definition, and then from there one can. Okay, so that completes the properties that we wanted to use. Now what we want to do is, before we go further, we want to make some remarks on something that I have already said. Remarks. The first remark is just now what I said. That is, without loss of generality, one can one could have restricted the definition of integrals. On x. That means we will go one more step and then define integral over E. The second thing that you have is that suppose E is a measurable subset of X. Then we can define a new measure space E measure on by defining this one measure of E or the sigma algebra ME is the set of all A such that A is. Now one can prove that ME is a on and then of course the measure does not remain unchanged. Okay, so we could be working on E, ME, mu restricted to. Okay, so that is possible and you get the same sort of results. So thank you very much. We conclude there today's lecture. We continue with it probably tomorrow or day.